Welcome to the webinar on Basic PET Physics and Instrumentation, Part 1. This webinar is brought to you by the European School of Nuclear Medicine in close collaboration with the International Atomic Energy Agency. In this webinar, I will address the basic physics behind positron emission tomography, and in particular, the physics of the positron emission and annihilation and the problem of the detection of gamma rays in time coincidence. We will also explore the factors that limit the spatial resolution in a PET image, both exploring the physics-related factors and the technological factors, and how this affects the PET image. We will also address information about the present technology for PET detectors that usually comprise a scintillator and a photodetection system. This is what we usually know about PET. We know that it is a molecular imaging technique based on the tracer principle that can provide different kind of information from functional, metabolic information, and various tracers are available for this. This is a list of examples from oncological to cardiological application, brain studies, and that all this information can be obtained in a quantitative way. But what is really behind all of this? What is the real objective of PET measurement? In positron emission tomography, or PET, a tracer labeled with a beta plus emitting radioisotope is injected into the patient. The actual objective of a PET study is the measurement of the activity distribution of this radioisotope within the body. This distribution can be described in terms of a function ρ of the spatial coordinate x, y, and z. In some cases, it can be also interesting to study the evolution of this distribution in time. This is the basic of the kinetic PET measurements. To understand how PET actually works, it is important to explain the basic physics behind the beta plus decay. The positron-emitting radioisotopes are atoms whose nuclei have an excess of protons with respect to the number of neutrons, and decay to a stable configuration through beta plus decay. In a beta plus decay, an unstable nucleus, X, reaches its stability by transforming one of its protons into a neutron. Hence, a nucleus X with an atomic number Z decays into another nucleus with an atomic number Z-1, together with the emission of a beta plus particle and an electron neutrino. A beta plus particle is the antiparticle of the electron, and it is usually called positron. A typical beta plus decay is, for example, the decay of fluorine 18 into oxygen 18. The beta plus decay is a three-particle decay. Because of its mass, the kinetic energy of the recoil nucleus can be neglected. Hence, the released energy is shared between the positron and the neutrino. When the positron reaches the thermal equilibrium with the surrounding tissue, it annihilates with an electron. In this process, the positron and the electron disappear, and all their mass is transformed into energy. This process is usually called positron annihilation. In fact, the product of the annihilation of a positron with an electron is the production of a pair of nearly collinear gamma rays of equal energy. From the Einstein's mass-energy equivalence law, the energy of both gamma rays is 511 kilo-electron-volt. Thanks to the nearly collinear emission of the gamma-ray pair from the annihilation of the positron with an electron, it is possible to define the line L along which the annihilation occurred. The line L is usually called line of flight, or LOF. The activity distribution ρ of x, y, and z is measured in terms of projections gamma and gamma gamma along lines L using the line integral operator. From the mathematical point of view, this can be expressed by the equation n gamma gamma proportional to the integral along the line L of the function ρ of x, y, and z. This is of course an ideal model. It assumes zero positron range, no deviation from collinearity, and an ideal behavior of the detector. This deviation from the ideal model will be analyzed later, looking into all of the terms that contribute to this deviation from the ideal behavior. So I can imagine to measure many projections within the body, so to measure many of this n gamma gamma, and then to recover the distribution ρ from these projections. This process is called image reconstruction. The image reconstruction description with all of its algorithms is not part of this webinar. Hence, from the instrumental point of view, the PET problem can be reduced to a detection problem. Hence, the objective of the measurement is then to obtain the spatial coordinates of the line L where the count is detected. This can be achieved by measuring, for both gamma rays, the coordinates pi of x, y, and z of the first interaction within a detector. A PET system is usually composed by a number of detectors surrounding the patient. These detectors have finite size, and it is not possible to infinitely sample the space for obtaining the projections. So it is necessary to define lines of possible combination of detectors. A line defined by a pair of detectors ij is called line of response, or LOR of detectors I and j. The pair ij is acceptable only if the detectors j belongs to an arch of detectors opposing to detector I, thus defining a sort of wedge, as shown in the picture. For example, detector 1 is allowed to measure a count along a line L only if the other gamma ray is detected by a detector belonging to an arch defined as in picture as arch 1. The same for detector 2, as shown in the picture, and so on. The intersection of all the similarly defined wedges is a region of the space where the sampling of the LORs is complete enough to permit the reconstruction of the PET image. This region is called the field of view, or FOV, of the PET system. Thus, summarizing the line of light and the line of response concept, it is important to remind that the line of flight is the line along which the two gamma rays are supposed to fly, and the line of response is the line connecting the two detectors where the gamma rays are detected. Then, due to the imperfection of the detectors, the line of response is not equal to the line of flight, and at the same time, due to the physics of the beta plus decay, the line of flight is not equal to the line where the positron emission actually occurred. Then, it leads to spatial resolution limitations. The best achievable spatial resolution in PET is limited due to both the physics of the beta plus decay and the available technology from the position detection of the two gamma rays in coincidence. So let's first introduce the limitation to the spatial resolution that are due to the physics. As we have already seen, positrons are emitted with a kinetic energy spectrum, and they lose their energy mostly through multiple Coulomb interactions in the biological tissue. For example, this plot shows the positron energy spectra of the most widely used PET radioisotopes. This process can be described by the so-called continuous slowing down approximation. A competing process is Bremsstrahlung, but it is more important at high energy. Finally, the positron reaches thermal equilibrium with the medium, and then an annihilation with an electron occurs. The total path of the positron is called path length, whereas the distance between the emission point and the position where thermal equilibrium is reached is called range. The range of the positron depends on the energy and atomic number of the medium. In water, the average range of the positrons emitted from mostly widely used PET radionuclides is about 1–2 millimeters, as reported in this table. This means that when we define a line of flight, it's not actually the line along which the emission occurred, but it is the line along which the annihilation occurred. And a certain distance is between these 2 points, and this distance is not negligible, thus leading to a limitation of the spatial resolution. To have an idea of the contribution of the positron range to the spatial resolution, and in particular the contribution to the full width at half max of the reconstructed PET image, one can remind that the final contribution will be the convolution of all the other terms, where the distribution of the annihilation points, as reported in this plot, for two typical PET radioisotopes. So one must note that the large contribution in terms at full width at 10 max with respect to contribution to the full width at half max. So the positron range contributes more to the tail of the image instead of degradation of the full width at half max, especially when low energy beta plus emitting radioisotopes such as fluorine-18 are used. Another important factor contributing the degradation of the spatial resolution in PET is the non-collinearity of the two photons. In fact, when the positron annihilation occurs with an electron of the medium, in first approximation it is assumed that both the positron and the electron are at rest. In this case, because of energy and momentum conservation, the annihilation can only generate two gamma rays of 511 keV each, that are produced back to back, as in figure 1 in this slide. However, this is not entirely true, because even if the positron has a thermal energy of about 1/40 electron volt at 27 degrees Celsius, that can be considered negligible, the electron is bound to the atom with an energy that cannot be ignored. If we consider the annihilation in the center of mass of the system, the collinearity and the equal sharing of energy is maintained. Since the laboratory reference frame, the center of mass is not at rest, but travels with a velocity v as in figure 2. The collinearity of the two photons will be lost due to the angle transformation from one reference frame to the other. This non-collinearity results in a Gaussian dispersion centered at 180 degrees of about plus or minus 0.25 degrees, more precisely 0.5 degrees of full width at half max, when a positron annihilates in water, as displayed in figure 3. The contribution of the non-collinearity to the full width of half max of the PET image can be expressed by the angular deviation delta theta multiplied by the scanner diameter d divided by 4. This is usually expressed as 0.0022 times the diameter of the scanner. The diameter of the scanner is then the critical figure for estimating the contribution of the non-collinearity to the spatial resolution. For example, for an 80 cm diameter scanner, which is a pretty clinical size, the contribution to the full width of max of the non-collinearity is 1.7 mm, and it is usually the most important contribution to spatial resolution degradation. In this slide, the two physical contributions to the spatial resolution are displayed in brief. In case 1, the line of response connecting detector A and B does not pass from the emission point because of the positron range. In case 2, which is related to photon non-collinearity, the line of response connecting detectors C and D does not pass from the annihilation points, and then does not pass from the emission point in turn. Of the two contributions, we have seen that the non-collinearity can be the dominating one because of the scanner diameter, but also the positron range can be important when higher energy beta radioisotopes are used, such as oxygen-15 and gallium-68, that has a very long positron range. We have already mentioned that the basic step in a PET measurement is to obtain the spatial coordinates of the line of response, where they count, corresponding to a positron emission and a further annihilation is detected. This can be achieved by measuring, for both gamma rays, the coordinates p of x, y, z of the first interaction in a detector. Hence, the ideal PET detector must be able to identify the position of the first interaction of a gamma ray in the detector itself, to measure the energy released in the interaction or in the series of interactions, and to carry information on the arrival time, at least for making the coincidence measurement possible, as we will see later. Various detector technologies can be used to provide all of this information. Many technological solutions borrowed from other fields of physics have been adapted for the use in PET, from wide chambers to solid-state detectors. However, the most common solution for a PET detector is, as of today, a scintillating material coupled to a photodetector system. Scintillation detectors are widely used in gamma-ray detection and form the basis for almost all PET scanners in use today. In fact, the most reliable solution is the use of a scintillating material coupled to a photodetector. Scintillation detectors consist of a dense crystalline material that acts as an interacting medium. When a photon of enough energy interacts inside it and releases all or part of its energy, the scintillator emits visible light, isotropically. The intensity of the emitted light, expressed as the number of low-energy light photons, is usually proportional to the released energy. The measure of the proportionality constant is the so-called light yield, and it is usually given in photons per MeV of released energy. The main advantage of the scintillator approach stays in the fact that these low-energy photons can be easily detected by a standard photodetector, such as photomultiplier tubes, and converted into an electric pulse. In this process, the original information on the energy released by the interacting photon is preserved. For this reason, and for the relatively high stopping power, mu at 511 keV, expressed like linear attenuation coefficient in the range of 0.3 or 1 centimeter to the minus 1 at the 511 keV for inorganic crystals, scintillators are widely used gamma ray detectors for almost all PET scanners. Important consideration when choosing the most appropriate scintillator for PET stay in the compromise among different features. Detection efficiency, expressed by the linear attenuation coefficient at 511 keV, and related to the crystal density and effective atomic number of the material, conversion efficiency, expressed by the light yield, and the time over which the light is emitted. The light is usually emitted with a fast light flash, followed by an exponential decaying intensity, with a decay time characteristic for each scintillator, from tens to hundreds of nanoseconds. For measuring the original energy of the incident gamma ray, it is essential that all the energy is released inside the scintillator. This can be done in a single photoelectric interaction, followed by a fluorescence emission, or in a multiple Compton scattering process. The occurrence of one or the other modality may affect the capability of measuring the position of the first interaction as required for PET. For this reason, the relative probability between the photoelectric and the total interaction in the scintillating material, called photofraction, is also an essential feature when choosing a PET scintillator. The table in this slide reports on the most widely used scintillators for PET. One of the main advantages of VGO is the very high attenuation coefficient at 511 keV. Another important feature is the very high photofraction at 511 keV that reaches about 40%. In recent years, VGO has been replaced by lutetium-based scintillators, and in particular by lutetium oxyaltosilicate, or LSO, doped with cerium, or lutetium yttrium oxyaltosilicate, or LYSO, again doped with cerium. One of the advantages of lutetium-based scintillators with respect to VGO is the very fast decay time, that is now 40 nanoseconds instead of 300 nanoseconds for VGO. Another important figure making lutetium-based scintillators so interesting is the light yield, that is about 4 times the light yield of bismuth gemanate. So putting all these two information together, highlight yield and short decay time, makes the lutetium-based scintillators ideal for PET. The light yield has influence in measuring the energy with a very high energy resolution, and together with the short decay time, it is ideal to measure the arrival time with great precision, then having a very high timing resolution. However, BGO is still used in modern PET systems mainly for its advantages in terms of detection efficiency. When used in combination with a scintillator, the role of the photodetector is to identify the position of the interaction within the scintillator itself, and to measure the intensity of the light that is produced in the interaction. The configuration of a scintillator plus a photomultiplier tube has represented for years the favorite solution for PET detectors. The block detector was introduced by Casey and Nutt in 1996 and still represents one of the most widely used solutions for PET detectors. The figure shows a scheme of the typical block detector. A scintillator block of about 40 mm side, 20 mm thick, originally made by BGO, is sewed up to a certain depth into smaller elements, usually and improperly called pixels. The empty space between elements is filled with a white reflective material to optically separate them and to ensure the maximum efficiency in light transport toward the photodetector. The light emerging from the scintillator is sampled by 4 square single-channel PMTs arranged on a 2x2 matrix. The position of the crystal element where the interaction occurs can be derived from the 4 signals produced by the PMTs using a simple formulas for x and y as reported in this slide, where Si is the signal produced by the ith PMT and E is the sum of all the Si values, and it is proportional to the total energy released in the scintillator. When made of BGO, to ensure a good spatial linearity, the saw cuts are deeper near the block sides and progressively more superficial as the cuts are close to the center. Clinical PET detectors still rely on the block detector, with increasing number of crystals per block of smaller and smaller size, down to 4 by 4 mm. When made by lutetium-based scintillators, the crystals are all separated from the adjacent one. X and Y, as obtained by the formula shown in the previous slide, are then the coordinates in the PMT space and are usually stored in a 2D histogram, usually called flood histogram, that, when obtained accumulating enough events, results in a series of peaks, each corresponding to a certain pixel. This representation suffers from significant space distortion with respect to the real position due to the poor spatial sampling, especially at the borders, case B in the picture, and corners, case C. In addition, peaks are broadened due to the statistical fluctuation of the PMT signals and the possibility of having multiple interactions in the scintillator block, thus resulting in some overlaps with the adjacent ones. The process of assigning a pair of x and y coordinates to an event occurring in a certain pixel is called pixel identification, and it is performed through the generation of a lookup table, i.e., a series of regions are drawn around the peak positions, filling the whole histogram space. Each region is then assigned to a pixel according to its position. Events generating an xy coordinate within a certain region are in turn assigned to that pixel. The limitation in spatial resolution of PET due to the physics of the beta plus decay have been already discussed. The best spatial resolution that is achievable from a PET system is also limited by other factors related to the detection process and the technology in use. The following considerations are elaborated for a pixelated detector block, as it is the most common configuration. Actually, when a coincidence is detected from a pair of crystals, they define a line response. For the finite size of the detectors, the halo R is not actually a line but a region, sometimes called a tuber response, where the annihilation has a certain non-zero probability to have occurred. This probability is described by coincidence response function. At the center of the FOV, the full width at half max of the coincidence response function is then equal to half the size of the crystal D. With similar consideration, one can understand that the full width at half max of the coincidence response function worsens by moving closer to one of the two detectors, as the function starts to be trapezoidal in shape. Thus, the contribution in terms of full width at max to the spatial resolution due to the finite size of the crystal is minimum at the center of the field of view and equal to d divided by 2. When the crystals in a matrix are separated by a reflecting material of non-negligible thickness, the value d is actually the crystal pitch, i.e. the crystal size plus the thickness of the separation material. The previous considerations are true only for phasing detectors, or in general, for pairs of detectors with negligible thickness. In fact, as the crystals defining the halo R are not lined, the finite thickness of the crystals comes into play, enlarging the domain of the response function. The lack of information on the depth of interaction in the crystal introduces a further contribution to the full width at max on top of the d over 2 term. This new term is usually indicated with the letter P and is called parallax error. In PET with ring geometry, the parallax error has a significant effect as images experience a sort of radial elongation. The contribution to the spatial resolution along the radial direction can be approximated by the equation shown in this slide, where R is the radial position where the point spread function is derived. Capital R is the radius of the PET ring, and alpha is a term that depends on the material and thickness of the scintillating crystal. For example, alpha equal to 12.5 for a 30 mm thick BGO crystal. The crystal pitch D and the parallax error P are both related to the geometry of the scintillator. Assuming that both crystal elements have been correctly identified, there are the only two contributions to the spatial resolution. However, some error may also occur in the identification of the crystal. When the crystal position is identified by calculating the centroid of the light spot emerging from the crystal by means of lookup tables, as previously described, there is a non-negligible position-dependent error called coding error and indicated with letter B. Another factor contributing to the coding factor B is the intercrystal scatter. Intercrystal scatter is an event where the gamma ray interact in a crystal, indicated in gray in the picture, suffer from a Compton scattering, and then it iterates again in another crystal, in the neighborhood, again indicated in gray. In a sense, intercrystal scatter is similar to parallax error. In this slide, you can see a comparison of two typical events. In both cases, the gamma ray enters in the crystal indicated by the green arrow, and after an intercrystal scatter on the left or a parallax arrow to the right, the interaction is apparently occurring in the crystal indicated by the red arrow. So in both cases we have a mispositioning with respect to the entrance point. And in both cases the effect is due to the physical properties of the interaction of the gamma ray with the scintillating material. By taking into account both physical effects and the technological limitations, the best achievable spatial resolution in PET can be summarized with the following formula, where 1.2 is a term related to the further degradation of the point spread function due to the non-uniform sampling of the linear responses in the field of view, and the image reconstruction process. This value is estimated assuming an analytical reconstruction algorithm, such as the filtered back projection. The factors in the quadrature sum are due to the detector size d, the coding error b, non-collinearity, where d is the scanner diameter, the positron range r, and the parallax error p. Various techniques have been introduced to reduce the effect of the technology-related spatial resolution degradation terms. For example, detectors able to estimate the depth of interaction have been proposed, especially in the field of preclinical systems. In this field, the spatial resolution that can be achieved is very close to 1 cubic millimeter, and this is very close to the theoretical limitation of PET. A simple way to improve spatial resolution is to use smaller pixels. Because of its moderate sampling, the standard 4 PMT's configuration of block detector is not adequate for reading out such finely pixelated matrices. For this reason, higher granularity photodetectors, such as position-sensitive photomultiplier tubes, have to be used instead. In Figure 1, you can see an example of these devices. The multi-anode photomultiplier tube H8500C by Amamatsu. In Figure 2, you can see how well a 1.7 mm pitch LYSO crystal is separated into small spots using this kind of PMT. These PMTs are widely used in the preclinical systems, but for the high cost, they were never used in actual clinical systems. In recent years, solid-state photodetectors are rapidly replacing photomultipliers tube for the design of PET detectors. The figures of merit to perform a comparison among the available photodetectors are the energy resolution, the timing properties, and the suitability for the use in hybrid PET-MR systems. The most popular solid-state photodetectors are avalanche photodiodes, or APDs, and silicon photomultipliers, or SIPMs. A first example is then the avalanche photodiode. An APD is a silicon-based device. In this table, a typical APD is compared with a PMT. The APD is really compact. and can be used to read out the scintillation light. In an APD, the signal generated by the incident light is internally amplified, typically by a factor of a few hundreds. Even though the signal of an APD is amplified by the multiplication process, it is not enough to be used without an external amplification in order to obtain a reasonable energy resolution, also thanks to the very high quantum efficiency. The noise level of this device is dependent on the bias voltage and on the temperature. APDs are then usually connected to a cooling system to stabilize the signal, thus improving the signal-to-noise ratio. In addition, they are quite slow compared to the photomultiplier tube, and hence they are not adequate for time-of-flight path. On the other hand, they are insensitive to magnetic fields, and thus can be used in hybrid PET-MR systems. Another example is the silicon photomultiplier. Now, let me briefly explain how a SIPM works. When the bias voltage on an APD is greater than the junction breakdown voltage, the charge multiplication is a diverging, self-sustaining process, called Geiger regime. This process results in a very high gain that can be quenched using a quenching resistor. A device based on this working mechanism is called single photon avalanche diode, or SPAD. An SIPM, also known as Geiger mode avalanche photodiode or multi-pixel photon counter, is a device obtained by connecting in parallel several miniaturized SPADs of few tenths of square micrometer belonging to the same silicon substrate, so that the output signal of the SIPM is the sum of the SPAD's output. The small SPADs in a silicon photomultiplier are named microcells. The signal produced is then proportional to the number of microcells that fire. If the number of microcells is larger than the number of incoming photons, the obtained signal is proportional to the energy released in the scintillator. In this table, silicon photomultipliers are compared to avalanche photodiodes. SIPMs are compact devices with single element size smaller than 1 square millimeter. They show high gain at few tenths of bias voltage, thus simplifying the front-end preamplifiers. The quantum efficiency, even if not extremely high, is still adequate to provide an excellent energy resolution. SIPMs represent an effective alternative to the current detectors used in time-of-flight path, because they have a very fast rise time due to the Geiger mechanism, with a signal rise time of less than 1 nanosecond for the more advanced devices. Compared to APDs, they have a slightly better stability with temperature, but usually they still require some temperature stabilization system. And finally, they are insensitive to magnetic fields. This feature makes SIPM the preferred choice for the design of hybrid PET-MR systems. Here you can see some examples from different manufacturers on how an SIPM device looks like. Note the extreme compactness of these devices compared to bulky photomultiplier tubes. In recent years, digital versions of SIPMs have also been produced. Digital SIPMs consist of an array of SPADs, each one equipped with a locally integrated active quenching circuit. Moreover, Additional circuits for digital processing, acquisition, and readout of the optical signal are integrated in the sensor. In the part 1 of this webinar, we have explored the basic physics behind PET, with a particular emphasis on factors affecting the spatial resolution in a PET image. We have also explored the detector technology for positron emission tomography. For further details on PET image quality, with particular attention to noise properties, please refer to part 2 of this webinar. Thank you for your attention.